RT.com. I'm Chris Sweeney, and today I'm joined by a very special guest, Mr. Chris Mason, who is a geneticist at Cornell University out in the United States. How are you doing, Chris?
Great. Good morning. Pleasure to be here.
Brilliant. Well, you've just released a new book, The Next 500 Years, Engineering Life to Reach New Worlds. Now, without taking the magic away, I'll let you explain it, but essentially you're saying that we as a human race need to adapt to live on a different planet, possibly, in time.
Yeah, so the premise of the book is that I wanted to lay out really what I believe and I think hope will happen for the next 500 years. It's very much a treatise for what is really possible, the human possibility. This includes not just the technology behind how we could get to another planet and survive there and eventually another star, but also I think the moral argument as to why we should go and why we have to go. And in particular, it's because we have a genetic duty, what I call deontogenic paradigm, where we have to protect, of course, ourselves. If we want to survive, we need to eventually get to another planet because the sun will run out of fuel. But also we have to serve as guardians and shepherds of all life. And so I kind of lay out a moral argument for why we should go and then get into the technology as to how we could survive.
Because I think your calculations or calculations that you're aware of is that we've got 4.7 billion years before the Earth is uninhabitable. So the 500 years, you see, if we start now, in 500 years, we should be able to start leaving this planet. So by the time the 4.7 billion years and Earth becomes uninhabitable, we'll be long gone.
Yeah, well, and a lot of people say, so there's 2 points to that. Is like 4.7 billion is kind of the maximum time. That's when the sun would engulf the inner planets. And by uninhabitable, I mean the entire planet would be lava, basically. So before then, though, it's interesting, when I wrote the last chapter of the book, I always had that number in my head for the last 20 years. I think, well, 4.7 billion, it's a long ways away. So it's not, it's not that urgent in a way. But as I was researching for the last part of the book, actually in about 1 billion years, the sun will get so hot, the luminescence will increase enough to probably begin to boil the oceans. And so it'll be hard to live if the oceans are boiling. You can maybe live underground for a while. But I actually reduced that time of what's our clock on Earth to probably like about 1 billion years, when it would just probably become too hot to survive. And that's assuming we don't screw anything up first, or we don't get hit by an asteroid, or other problems emerge. So, even though 500 years versus 1 billion or 4.7 billion is a really stark difference, this assumes that nothing else goes wrong, which we've been hit by many asteroids over the past 4 billion years, and we know that the Earth has been bombarded and continues to be bombarded by things from space. So it's and there's also that we could screw something up too. You can never look past that. But I'm hopeful that we won't, and I know that we can. And after about 500 years, have all the technology to go towards other planets and even stars. Because
also another part of the book, the survey you were involved with in NASA, when a set of twins, one went up to space and one stayed in Earth, and you compared them after a year. And I think probably it's not just going to other places. We're not able to go to other places at the moment, are we? Because our bodies would break down, as it was shown in that study you did with NASA.
Yeah, the body, as we described in the twin study and other subsequent missions that we've done with NASA, is, of course, the body's very adaptable. When you get back from space, it essentially can get mostly back to normal. Even within a few days of being in space, the body can adapt. But it's not pleasant. It's very hard on the body. If you look at the molecular signatures of spaceflight, they look a lot like what do you do when you're fighting a really bad cold, or when you're even fighting a severe injury in the body. So it's clear that the body is fighting. The immune system is on high alert. You're trying to adapt to a very distinct and unusual environment for the body. But it can do so. But we know that it can do it, but it has never been engineered to do so. It's doing it kind of accidentally and making it work. And so one of the premises of the book is, well, could we take lessons from other creatures and think about ways to maybe do it better, or to keep astronauts safer for really, really long missions?
And you also talk about sort of I think one thing very interesting with the vitamin C, that we can actually make vitamin C ourselves, but the genes sort of been turned off. So, with the stuff you're working on, so you would start to sort of change the DNA of humans, and would we still look the same? Would we still be the same? How's this going to play out, sort of thing, sort of down the line?
Yeah, so I propose to do, so I propose there's things we can do. There's a chance that we start to send people into far deep space, and maybe we don't need as many modifications as I think. Maybe we'll be just fine. The human body is extraordinarily plastic and adaptable. The biggest threats, though, are radiation and also the lack of resources. And so to the point of, well, what could we change? Let's assume we reach a state where we say, the body's not built for it. We need to change something. What can we change? So, yeah, as you alluded to, we do still have the gene to make our own vitamin C. It's called gulo, and it's in our DNA. It's in a broken form, basically. So if you look at other primates or other, like cats and dogs, for example, they still make their own vitamin C. So you don't have to worry about scurvy for your dog because it can make its own vitamin C. And other primates still can, but most of us with dry nose primates is called haplorhines versus wet nose primates. They can still usually make their own vitamin C. So it's relatively recently in evolution that we've just branched off, and because there was enough of it in our diet, it's no longer was selected for. So it just kind of faded away. But the gene is still there. The relic of a function we used to have is still in our DNA. And so in some cases, I'm thinking about, well, why not we just take what we know works therapeutically. Sometimes you can activate a gene, or you could CRISPR it, other ways to just turn something back on as a therapeutic. In this case, it'd be turning a gene back on for nutrition. But one example is for treating certain blood disorders like beta thalassemia. You can turn back on a fetal hemoglobin gene. And there's different kinds of hemoglobin. When you develop as a fetus, you have one kind called fetal hemoglobin. You're an adult, it's called adult hemoglobin, that carries the oxygen in your blood. But one of the therapies that's in the clinic today is, well, let's just turn back on the gene that got turned off once you got born, called fetal hemoglobin. So this idea, everything in the book is anchored on science that exists today, on clinical trials that we're doing in my lab or with others. So this is what's kind of fun about the book is it's not science fiction. It's all anchored and built on tools and technologies and clinical work that we do today.
We wouldn't look any different, or we wouldn't be kind of superhuman. Like, we wouldn't be able to put our hand into like molten lava and survive it. A bit like Snow. I don't know if you've seen the show Snowpiercer, where they create the guy and he can go outside in like minus 200 degrees and he's fine. So it's not that kind of stuff. We wouldn't actually look any different to the eye.
Humans are always evolving, including today. So we, invariably look different from how Cro-Magnons did. And how other Neanderthals. So we will continue to change and adapt and evolve. It's just a question of how fast and over how long does it take before we look different. And especially if you're thinking about adding new genetic components, it'll probably accelerate that process. But will it be 10,000 years? Will it still take 1 million or 2 million years? It's hard to say. But certainly if you're on an entirely different planet with significant changes to the genetic code, that will accelerate some of the processes of evolutionary differences, I would think.
And are we going to need a lot of kind of pioneers to do this? Are we going to need a lot of people to sort of sign up and sign their body over to science, knowing that they may not come back? Because I guess if you're sending someone into space and changing the genetics, any science can always sort of a bit of trial and error. I guess are we looking at finding human volunteers? Just thinking that would that be quite difficult?
There'll be I think we won't need anyone soon. I think a lot of the missions in the next 5 to 10 to 20 years will still be relatively short. But in about the first boots on Mars are supposed to be by 2035. China might get there. Some of their latest announcements, they said by 2031 or 33. So, that's not that far away. Most of those missions will be return missions, though. So you'll go and come back. But I think we will, within about 20 years, have to really look at this question of what if someone goes to go permanently and stay as be on Mars, or if not permanently, to stay there for 5 years or for long durations. We, it won't be anyone that's probably in the Navy today or in the astronaut corps. It'll probably be someone who's 10 years old today, who will be the person that would be selected 20 or 30 years from now to go to some of these really hard missions. But, so millions of people apply to be astronauts every year. And the rate of we should look up the exact number. I think it's basically like 1.6% of people who've ever gone up in space have died, right? So that's a pretty, it's pretty high odds for just dying, like something exploding, something going wrong. So, and everyone wants to go. So I'm not too worried about people signing up. I'm worried about making sure that we have rigorously demonstrated safety and efficacy for anything before we deploy it to an astronaut. But that's happening now. We're trying now.